everyone. Welcome into lecture number 6 of differential equations. This lecture is on exact equations. So let's start with a motivating example. And we'll see exactly what we mean here. But this is a motivating example. Let's consider the differential equation of the form 2x. So this is an equation in terms of x's and y's. But 2x plus y squared plus 2xy y prime equals 0. And notice that this equation is not linear, for sure. We've got a y squared here, so it's not linear. There's also a y times y prime. So it's not a linear equation. And it's also not separable. You could take some time to try to rearrange this, but it's not going to be possible. So it's also not separable. And these are the two types of equations that we know how to solve so far, right? Linear and separable equations. This one is neither, actually. It's neither case. So what can we do? Well, let's suppose that near any initial value that we want any initial point, right, that we want to try to solve this equation around, let's suppose that our solution can be considered as a function, y is a function of x, right? So our solution curve is a function of x, all right? And in this case, let's also then observe. So this is why this is a motivating example. I'm going to kind of just give us a solution, and we'll check that it's really a solution, but this will motivate the rest of our study. So at this point, let's observe, again, keeping in mind that y is assumed to be a function of x in this equation that I'm about to write, let's observe that the function c of xy is equal to, so x squared plus x times y squared, obeys the following properties, all right? And I'm going to do some things here that are technically Calc 3, but again, we talked about partial derivatives a little bit in the last lecture. We're going to use partial derivatives again in this lecture. Anything that we do with partial derivatives is just going to be straightforward computation. So if you haven't seen them yet in your other studies, don't worry too much about it. I'll try to make clear exactly what we're doing here. So here's what we're going to observe, that this equation, if we take the partial derivative, and again I'll tell you what that means, but the partial derivative of this function c with respect to x, the way that we do this is we just look at this equation and we take the derivative of the x variables and we consider the y's as constants. That's why this is called a partial derivative. So we kind of ignore the y's, but we treat them as constants. So when we take this derivative, the derivative is going to be the derivative of x squared, which is 2x, plus the derivative of x times a constant. Well, that's just going to be the constant, and in this case, that constant is y squared. So we have deep c dx is equal to 2x plus y squared. And on the other hand, we can do the same thing with respect to y, right? We can take the same point of view, take the derivative of this function c with respect to y and treat the x's like constants. Well, in that case, the derivative of x squared with respect to y, that's a constant, right? So its derivative is 0, so that's gone. And then the derivative of this term is going to be constant x hangs around times 2y, or we could write it as 2xy. All right? And notice that these are exactly the terms that we have up here in our differential equation, right? So this is where we're making our observation. So we have this term here, and then this term is multiplied by y prime, all right? And so that means that with respect to this function, c, we can rewrite our differential equation now, right? So plugging in to the original DE, remember DE here just means differential equation, we can again replace what I've highlighted here by these terms, right? So I can replace that whole term by this deep c dy, and this whole term out in front here by deep c dx. And so this equation now becomes, let me write the whole thing, but 2x plus y squared in parentheses plus 2x times y prime equals 0. Remember, y prime here means dy dx, so we're going to rewrite it in a minute, actually. But making our substitutions based on the function that we found here, right? This is going to be deep c dx plus deep c dy, whoops, times y prime. But again, we can write y prime as dy, regular dy by dx, right? It's just a derivative, dy by dx. So we can just change the symbolism there. And this has got equals 0. And now it turns out, and again, this is a result from that you'll study in more depth in Calculus 3, but it turns out that this right here, this term right here, because we made this assumption up here that our function y is actually a function of x, then we can regard, in this case, so if we go back up here, we can regard, because of this assumption, right, this means that we can regard our function deep C of x and y, this looks like a function of two variables, actually as a function of just x and y of x, right, and we can regard it just as a function of x, okay? And again, if you've taken Calc 3, then you'll recognize that this is then the chain rule. This is the chain rule for the derivative of c with respect to x. And so this whole term right here is just deep c dx with a regular d, a regular derivative of deep c dx. If you haven't taken Calc 3 yet, then you're just going to trust me, and we're going to develop a systematic way to solve these equations where you don't actually have to know all this theory, okay? But this motivation, though, is going to lead us to that general solution in a few minutes. So anyway, this is the chain rule, right? So this, what ends up happening is that we get here that this becomes deep c by dx equals 0. So this was, again, remember, this was our original differential equation rewritten with the function that we found, right? And so we've now gotten to this equation, and this is obviously separable, and it's very clearly separable, right? So what we end up with here is this becomes deep c equals 0 dx, and we can integrate both sides. All right, and this deep c right here, this is called an exact differential. All right, and so this is exactly what we're looking for here. So let me write it this way. If we were to multiply through dx by everything, then we could write it this way, right? So deep c equal to partial of c with respect to x times dx plus partial of c with respect to y dy. This is called, if you can find a function that obeys this, right? And so that's called an exact differential in the context of this class. All right. So this is why we're calling this section exact differential equations. So we now have an exact differential equals to 0, right? When we integrate both sides, our solution. So, and again, this is going to be implicit, right? The implicit solution. Implicit means that the y is going to be probably wrapped up in here somewhere, right? Is going to be the following. Well, if you integrate a differential, you're left with just the function, right? So our solution is going to be c of xy. That's our function that we found up above. I'll write it in a minute in relation to this problem. I'm trying to mix together some abstract ideas with our specific problem, right? But just abstractly, you integrate deep c and you get the function c of xy. And then on this side, you integrate 0, right? And you end up with a constant. So there's an unknown. There's the unknown constant of integration right there. So that's why this is a general solution. And if we go back up to our given problem, right? So this problem, then we see, all right, our function c was this, x squared plus y squared, x squared plus x times y squared, right? And so this is the solution function, actually. As an implicit function, notice the y is not solved for explicitly, right? And so for this problem, we end up with this solution. Let me rewrite the whole problem. Right, so for this problem, the equation was 2x plus y squared plus 2x times y prime equals 0. And this has the solution, or solution set really, right, of our function, which was x squared plus x times y squared equals c. And this is for real numbers c. So the reason it's a solution set, right, is there's infinitely many possibilities for c, but this implicit equation, the functions determined by this implicit equation here, solve this differential equation that we were given. So that's the idea. This left-hand side, this is our c, right? So we just highlight this is equal to this. All right, so that's the idea. Now, obviously the question is, where did this function come from, right? So I just kind of gave us this function in this motivating example. The question for the rest of this lecture is going to be, how can we find this, right? Can we generalize this, and then how can we find this function c that's going to solve our differential equation? And so that's what we'll focus on for the rest of this lecture here, how to actually do it. But this is the theory of what we're trying to do. All right, so what we're trying to do. All right, so for item 2, we want to generalize this from this specific example. So here's a generalization, and this is going to end up being a theorem. I won't prove this theorem, but you can find proofs. It's not too hard to prove it. But I would like to focus on the actual solving of this. So here's what the theorem says. It says let the functions, and I'm going to have some partial derivatives involved in these functions now. So the functions m, n, and then dm by dy and dn by dx. So m in this scenario, m and n are functions of both x and y, and these are the individual partial derivatives of the first one with respect to y and the second with respect to x only. And suppose that these are continuous. So we're saying let these functions be continuous in the rectangle, or in a rectangle. And this is very similar to our fundamental existence and uniqueness theorem statement for the general case, right? So in a rectangle given by the following. So the x values are between alpha and beta, and the y values are going to be between gamma and delta. All right. So this is the only criteria, that these four functions be continuous on this rectangle. Then, in this case, the equation is exact. And I'll interpret this, but it means, in other words, it means we can apply the logic that we just used, right? So the equation is exact. So let me write the equation first. So the m and the n are going to play a role in our equation, right? So the equation is m of xy plus n of xy y prime equals 0. So this equation is exact if and only if the two partial derivatives are equal to each other. So if dm by dy is equal to dn by dx in all of R, so in the entire rectangle R. All right, so on this entire rectangle. So the equation, you could say, is exact on the rectangle if the partial derivatives are equal on the rectangle. All right, so let's interpret this. Well, what does it mean, right? So this whole definition of exact, what does it mean? It means that the left-hand side obeys this relationship right here that I called an exact differential. All right, it's not quite written as a differential in this form, right? So let's interpret this. So our interpretation is the following. So again, there exists, this is not the theorem, right? But there exists a function c of xy defined on R that satisfies the following. So satisfying this property, that the c dx is equal to m, and the c dy, partial derivatives, is equal to n. And so this means that this equation, which I'm going to write, so I'm going to write this out in two steps, okay? Just so we can see exactly how this works. So remember, this is the differential equation that we're given. So this can be written, first of all, this y prime can be replaced by a dy by dx. And if we think in differentials, we can multiply the whole equation by dx, right? By a tiny, tiny change in x. So this equation becomes m of xy dx plus n of xy dy equals 0. All right, and again, the left-hand side, if we have this relationship, which is what we're saying, that's what the theorem is telling us about, right? Then we can rewrite this entire equation as deep c dx times dx plus deep c dy, partial derivative times dy, equals 0. And this is where the language of the exactness comes in, right? Because now this entire term is the exact differential that we've kind of implicitly defined up here. This is the exact differential, and that can all be replaced by deep c, right? So this Greek letter is c. All right, and so this means then that we just have this equation right here. Okay, so the question still is, how do we find deep C? But it comes from these two equations right here, actually, that we just wrote down. But this is the idea. And so once we have this, then the solution, in this case, once we've verified that we have an exact equation, we can try to find this function, right? This function c of xy. And all we have to do then is integrate both sides. And the solution of the exact equation is then c of xy equals to a constant, right? And if you have an initial condition, then you can solve for this c, the c, the actual constant c. All right, so let's talk it through here with an actual example where we have to actually find the function. It's not given to us, right? By the way, if you have taken Calc 3, remember I said that Calc 3 is not a prerequisite for this course, and so there's a lot of notation from Calc 3 in this build-up here, in this setup, the motivation of this method, this exact differential method. So if you haven't taken Calc 3, you're probably like, what the heck? But if you have taken Calc 3, you're probably wondering exactly how does this all tie in, right? So if you have taken Calc 3, the relationship here is that an exact differential corresponds to, in some sense, it corresponds to a conservative vector field. Okay, so an exact differential has a really close relationship with a conservative vector field from Calculus 3. And so the function c here is like the potential function of the conservative vector field. All right, so differentials, again, this is something that you get into in Calc 3. So it's not required for this course, but if you've already taken it, differentials are like, they're kind of like the cousin or the brother or sister of vector fields in Calc 3. And so this exact differential corresponds exactly, pun not intended there, but the exact differentials correspond to conservative vector fields, and then both of them are related to this function c is called the potential function for either one of them, for the vector field or for the differential. All right, so our job is to find the potential function in the language of Calc 3 here. Find the potential function c. All right, so let's just do it, and I'll stop talking about Calc 3 now. But let's just do this. So as our first example, I'd like you guys to verify that this equation is exact, and then we'll come back and we'll solve it together. But this differential equation is going to be y cosine of x plus 2x e to the y, parentheses, right? And then plus, parentheses again, sine of x plus x squared e to the y minus 1 times y prime equals 0. All right? So I want you to guys to take a moment and verify that this equation is exact. So apply our theorem. Identify the functions m and n, take the appropriate derivatives, and check that those are equal to each other. And once you've verified that it's exact, come back and we'll solve this one together. Alright, so hopefully you guys have verified that this equation is exact, but let's start off by verifying it once again together. So you guys have already done this part, but let's just check and make sure that we're all on the same page. So the function m is this first one, right? So it's y cosine of x plus 2x e to the y. And the function n, kind of like the coefficient function of the y prime, this is sine of x plus x squared e to the y all minus 1. And we need to take the appropriate derivatives, right? So if we were to write this equation in differential form as opposed to derivative form, I'm going to do it, right? Then the y prime becomes just dy, and this becomes dx, right? So again, we're thinking in exact differentials. If we scroll back up to like right here, if we think in this differential form, then what we have to check to make sure that this equation is exact is we have to take the kind of the opposite. This is our m, right? And this is our n. So the m is in the x spot and the n is in the y spot. We need to take the opposite partial derivatives to check that that this equation is exact. So we're going to take dm by dy, right? The partial derivative with respect to y, the opposite slot that it's in. This is going to leave us with, if we just look at this, it's going to be cosine of x plus 2x e to the y, right? E to the y is its own derivative. X is a constant. Behaves like a constant in this case. Cosine of x also behaves like a constant. So there's the derivative dm dy. We also need to take the derivative of n, this coefficient here, this function, with respect to x now. So dn by dx. Well, the derivative of sine is cosine. That's good, right? The derivative of this term is 2x, and then this is a constant, so 2x e to the y, so that's good. And then the derivative of a constant is 0, so this is 0, right? And so at this point, we can subtract these. I mean, we can probably see that these are equal to each other, but if we subtract these, then we can write this dm by dy minus dn by dx. This difference is then equal to 0 minus 0, so this is 0, right? And so this is criteria. This is the same exact thing as saying what our theorem said, right? That dm by dy equals dn by dx. Right? If their difference is 0, then they're equal. So that's it. So this means that our equation is exact. All right, so that's what you guys should have done before you came back from the break there. Now what we want to do is actually use this information to solve our equation. So we need to find that potential function, as I called it, that function psi. All right, so what we have to do now is recall that in this scenario, right, that this is the solution. So our psi dx is equal to m and psi dy is equal to n. So we have basically two differential equations. They're kind of with respect to different variables, but we'll see that we're going to get one function out of this, right? So on one hand, we have psi by dx is equal to m. So now we're back in the same variable, right? After we've checked that it's exact, we go back to the same variable. And so what this means then is that partial psi is equal to m partial of x, right? And so what we can do is we can integrate both sides, and we get kind of a partial answer. There's partial differentials here, right? So these are not total differentials. So what we end up with is that one equation for psi of xy is that it's equal to the integral of this m function, y cosine of x, plus 2x e to the y, integrated with respect to x. Okay, I'll just put a regular d here. But let's see what happens when we do this. So we integrate this, and look what we're integrating only with respect to x. So this is like a partial integral. So when we integrate with respect to x, the integral of cosine is sine, right? So we end up here with y times sine of x. The y is a constant. Plus the antiderivative of 2x is x squared, right? So here we have x squared e to the y, and then we have plus a constant, right? But this constant, because the integral is only with respect to x, this constant, I'll call it C1, could involve y's, because this integral sees y's as constants, right? So actually this constant could be a function of y. It's not going to involve x, but it could involve y. All right, maybe it doesn't though. But let's see what happens with the other function now. So now what we have to do is integrate n with respect to y and then compare, okay? So same deal. I wrote the wrong letter here, but psi dy should be equal to n. And so again, this means that partial differential here, psi, should be equal to n partial y. And then when we integrate, we do a partial integral, and we just, in an integral, we usually just change this to a regular d. But the point, though, is that our function, psi of xy, is equal to not only what we have up here, but it's also equal to the integral of n, whose equation is sine of x plus x squared e to the y minus 1, integrated with respect to y, okay? And so we go through kind of the same steps, but with respect to y now. So integral of sine of x with respect to y. Well, that's a constant, so the integral is y, or the antiderivative is y times sine of x, plus integral or antiderivative of x squared e to the y. X squared is constant because it's x, right? E to the y is its own antiderivative, so this is x squared e to the y. And then the antiderivative of 1 is y. All right, and the same deal. This could have a constant, but this constant could depend on x, right? Because this integral, this partial integral here, will not see x's. It'll see x's as constants. All right, and so at this point, these are two different equations for our function that we're looking for, our function psi. All right, so we have these two different equations. So they're both equations for psi, right? And so then we want to match them up. So what do we have? Our psi needs to have this y sine of x. Okay, good. So there's one answer. So that's the same, right? We need that. It's there. It also needs an x squared e to the y. Good, we got that, right? It also needs, let's do magenta. It also needs a minus y. We don't have a minus y in the first one, but that's because the minus y must be wrapped up in this constant function, right? In this function. So we need that. We need the minus y. And then on the other side here, the last thing is this constant with respect to x. So do we have any functions of just x in the first one that we're missing? No. And so what does that mean? Well, we can just cancel this out. We don't need that extra constant function there. It's not really constant, right? We don't need this extra function of x. However, we do need the function of y, right? So see the difference there? We needed to make this one equal to minus y. We don't need this one because we're not missing anything. And so the end result here is that we take one of each color of this, right? So our solution then is that our c of xy, this function is equal to y times sine of x. So we're not adding these together, right? We're just taking one copy of each because they each equal to the same function. We don't want two of these. We just want this, right? So it's y sine of x plus x squared e to the y. We've got that, right? Minus y. We need that. And that's it, right? And so our solution is that this equals to our unknown constant. And so there we go. There's our solution, our implicit solution to this differential equation. This was our differential equation right here. All right, so there's the solution. All right, so that's how that works. Hopefully that illustrates the process for us of how to do this when our equation is exact. The next question we want to ask is, what happens if the equation is not exact? So this next item, which we'll number 4 here, this is going to be called integrating factors. And this should remind us of how we dealt with linear equations, right? So when we had a linear equation that was not separable, we tried to make it separable by multiplying the entire equation by a non-zero integrating factor, a positive in that case, right? Positive function that acted as an integrating factor. So let's suppose we have the same situation, but not with, same type of situation, but with a potentially exact equation. So an equation in this form. So m of xy plus n of xy times y prime equals 0. And suppose that this is not exact. It's not exact. So the question becomes, and our goal becomes, can we find a positive function? Right? A positive function, which we'll call mu of x and y. So this, a priori, meaning at the beginning of this, at the outset of this investigation, this function could be a function of both x and y that will make it exact when we multiply through the whole equation, right? So the same exact idea that we used when we solved our linear equations. So I'm going to label this equation star. So we're going to make this exact when multiplying through, right? This is our goal. And of course, this then is going to give us some criteria for what kind of function this mu has to be. So let's just say this. Let's investigate, right? What are we going to do? First, we're going to multiply through. I'm going to drop the independent variables here, even though y is not really independent in some sense, because we're trying to find, we're assuming that y is a function of x, at least in a tiny neighborhood around the point, when we think about our fundamental existence and uniqueness theorem. But for the sake of this argument, let's just drop the arguments. And we'll write this then as mu times m plus mu times n times y prime equals 0. So what have I done here? I've just multiplied the entire equation star by mu, right, to get this new equation double star. And the idea here again is that mu is a positive function, therefore it's never 0, and multiplying through by it does not change the solution of our differential equation, right? And so at this point we can kind of regroup, and we can consider these functions to be like m hat and n hat, right? And if this equation is going to be exact, then these partial derivatives have to be equal, right? So for equation 2 star to be exact, which is our goal, this is what we want, then dm bar by dy has to be equal to dn bar by dx. Same deal, right? But remember, mu is a function of both x and y. So let's work this out and see what kind of equations we get. So first, dm by dy. This is the y partial derivative of the product of mu times m. And so the product rule must be applied, right? And so what we end up with is partial d mu dy times the function m plus the function mu times the partial, the m dy. All right, we can do the same thing for n, right? So the n bar dy is going to be equal to the, this is with respect to x, right? The n bar dx is going to be equal to the x partial derivative of mu times n. Mu is the same function. This time we're taking the x partial derivative, so d mu dx times n plus mu times dn by dx. All right? And so these are supposed to be equal to each other, or we can do the same trick we did before, which is subtract these and set that difference equal to 0, right? So our goal is to get the difference to be equal to 0. And what we end up with, if we work this out, is the following. So we're going to have this difference here, right? So we'll have a difference. d mu by dy times m minus d mu by dx times n plus mu times, so I'm factoring out the mu, and then the difference I'll take of these two. So this will then be d mu dy, sorry, that's an m, dm dy minus dn dx. And this is exactly what we had before, right? dm dy minus dn dx, and this should be 0. And remember, if from the beginning, if our equation was not exact, right? If our original equation was not exact, then this difference is not 0, right? So this assumption that this is not exact, this means, so this assumption right here, let me highlight it. This assumption right here, that our original equation is not exact, this means that this term, right, is not equal to 0. So that one is not equal to 0 by our assumption. And so what we can do then is solve for mu, and we'll get kind of a little bit crazy, but we'll get a differential equation for mu here. And we can write this as follows. So just rearranging, we'll subtract this, so that's going to change the order of these two when we move it over, and then we can divide by this term, right? And so our mu of xy must satisfy, for this whole process to work, right? It must satisfy the following equation. So mu should be equal to this difference, so it's going to be, again, when you move it to the other side, it's going to change the order, right? So it's going to become d mu by dx times n minus d mu by dy times m divided by this term that we're used to, right? So this is the one, this is the non-zero difference that we would check in the first place, right? To check if the equation is exact in the first place. So d mu dy minus dn dx. And so there's our mu. This is an equation that mu must satisfy, and it's a kind of a differential equation. It's got differentials here, right, or derivatives here, but the derivatives are mixed up with respect to x and y, right? So let's make a couple of assumptions now. So there's two different possibilities that we're going to be expected to deal with on our own here. But one is that let's suppose that mu is simply a function of x. In other words, mu does not depend on y. All right, mu does not depend on y. So what this means then is that d mu by dy is equal to 0, right? If mu does not depend on y at all, then its y partial derivative is 0, and this term is gone, right? This term is gone now. And so what we end up with then is that mu, in this case, mu would have to be equal to d mu by dx. That's just the regular derivative because it only depends on x, right? Times n divided by this term, right? So divided by our difference, d mu dy minus dn by dx. All right, but actually if we want to solve this, what we really should do is solve for the derivative and make this a differential equation with respect to mu, or for mu, right, with respect to x. And so we can just multiply, we can just kind of swap these, right? So I'll highlight them, but we can swap all of this with all of this, and we can rewrite this then as, again, this difference shows up. I'm going to always try to keep this difference in this order because this shows up in all the calculations that we do. So dn by dy minus dn by dx over n in this case, right, is equal to 1 over mu times d mu by dx. And so at this point, you can see that this is now a differential equation for mu. It is separable, right? So we can separate this, and we will have, solving this, I'll write it in 2 steps, but 1 over mu d mu is going to equal, again, this ratio, dm dy minus dn dx, all over n dx. And then when we integrate, we solve this one, we're going to get a log of mu. We raise it to exponential, right? And so what we end up with then is, if we were to call this, and our text does this, but if we were to call this function right here q of x, if we call this q of x, right? So it's got to be this has to be a function of x for this to work, right? So part of our supposition here is that mu is only a function of x, and therefore, by definition, this must be a function of only x. So, you have to check this. It might not always work, right? But in this case, if it does work, then this is a function of just x. And what we get then is that mu is equal to e to the integral of q of x dx, where q of x is equal to, again, that ratio, dm dy minus dn dx over n, and this is a function of only x. All right? So in other words, no y's in this function. Function of only x in that one. Okay, so this becomes the integrating factor. Now, I did that kind of a roundabout way. It's, it's just basically just working out the definition here. So what do we want? What happens? What are the consequences? We solve for mu, but in reality, mu then has to solve a differential equation. So the right thing to do is to solve for d mu dx, actually, right? And then as we work through it, we end up with this differential equation, and this is the solution, right? Provided that this orange q of x here is a function of only x. Now, case 2 would be that the same thing would be true, right? But it would be true with respect to y. So in this case, I'll let you work out the details here. I'm going to make this a recommended exercise. All right, but in this case, the following would be the true, right? So let's say we called this one q. So let's call this q hat. If q hat of y, so if this function right here is a function of just y, so again, it's going to be this dm by dy minus dn by dx over negative m. So if this is a function of only y, if this is a function of only y, then all of the work that we've done up here, so then that means that our mu is just a function of y, and its solution is going to be very similar, right? So this is a different function. Notice the minus sign here. So when you work this out, you'll see that you get a different sign because something else it's from this step right here. You get the opposite one being canceled out. You get a minus sign right here from this step. Okay, but just work this out very carefully. And so what you end up with then is that your integrating factor can be done as a function of y, all right, and it's going to be equal to e to the integral of q hat y of y dy, all right, where q hat is equal to this function. All right, and so that's how we can find the integrating factors as functions of just x or just y under these specific criteria, right? And so again, in this case, the criteria is that this one is just a function of x, and the other possibility is that this function, which is different, right, is just a function of y. They probably won't happen at the same time, right? So it's a matter of choosing the one that fits our scenario, and if it doesn't fit either scenario, then it's going to require extra work, and in this class, we'll be given the integrating factor if it doesn't fit into either one of these scenarios. Okay, so let's end this lecture with an example of finding an integrating factor and solving an equation that's not exact by making it exact. So here's what I'd like you guys to do. So go through this whole process. I'll just tell you, you're going to want to use this case 2 on this one, just as a hint. But let's work this one out then. So here's the differential equation. It's y plus 2xy minus e to the minus 2y all times y prime equals 0. All right, so I'd like you guys to solve this one by finding an integrating factor. and then making it exact. So solve by finding an integrating factor and then making this exact and going through the whole process that we've just gone through. So take a few minutes, pause the video, work this one out yourself, and then come back and check and make sure that you've got it correct. All right, let's see how this went. First of all, we need to identify what are currently the functions m and n. So the function m is just y, and the function n is 2xy minus e to the minus 2y. Remember the functions that we need, so the derivative functions that we need are dm by dy, which in this case is just going to be 1, right? And then we need dn as a derivative with respect to x, so dn by dx, that's just going to be 2y minus 0. And obviously this difference is not 0, right? So this difference, dm by dy minus dn by dx, is 1 minus 2y. That's obviously not 0, right? It's not identically 0. Okay, so we go back up and we look, we want to make an integrating factor, right? So which equation do we want to use? Well, I gave us a hint that we should try to use this one. Okay, try to use this one. And the reason that we can tell that this one is going to be useful for us is because of the form of this difference equation, right? So notice both equations for Q and for Q, so for Q and for Q hat down here, they both involve this difference that I've just written down, right? So every time we take these partial derivatives, we subtract them, we get this difference function. In this case, it's going to be divided by n, right? If we want this to be a function of just x, well, n has, okay, it has x, but it also has y. It's not going to cancel this. It's going to be, you know, a little bit complicated. Maybe we could do some simplification, but honestly, with the e to the minus 2y, it's probably not going to work. The other one, though, q hat, is divided by minus m, and that one is just y, right? So it'll be just minus y. And this is already a function of just y, so this looks good, right? So let's use that. So that's how we would determine which one of these two cases to use. We look at the form of this difference equation, dm dy minus dn dx, and then compare it with, you could write them both down, right? But compare it with the functions n and m themselves, right? So we'll make our function q hat of y because we've observed this. We didn't write a whole lot down. But remember, q hat of y is dm by dy minus dn by dx. I recommend writing this down as, you know, every single time you use it, over minus m. Remember that has a negative sign, it has to. All right, and so this is then going to be 1 minus 2y divided by negative y, and then we can rearrange and solve for this, right? So this is going to be 2 minus 1 over y. All right, this is just q hat. So now our differential equation for mu is that 1 over mu d mu by dy is equal to q hat of y. All right, we can go back up and see that. So it would be from this step, right? There would be 1 over mu d mu equals q hat of y dy. So this is part of the recommended exercise of working out the formula with respect to y. But it's very similar to this, it's just with respect to y. And so, of course, this is then going to give us 1 over mu d mu is equal to q hat of y dy. And eventually we get to exactly this formula, right, for mu. So I'm working out steps that you should have already done in the build-up here, but that's okay. So this is then going to be, we're going to get that our mu, after some steps, right? So I'll put dot, dot, dot. So after some steps, we're going to get our mu is equal to the integral of 2 minus 1 over y dy. And so this is going to be e to the 2y minus natural log of y. So this is then going to be 1, so this will be e to the 2y, that's fine. This is going to be 1 over y, right? E, so let's break it up. E to the 2y times e to the log of 1 over y by log rules. And so this is just 1 over y, e to the 2y, y's got to be positive here. Okay, so remember we want a positive function, so there's our restriction. So there's our mu. Now what do we do with the mu, right? So now we've got our mu. Now we multiply our entire differential equation by that mu. So it's going to be mu times y plus mu times parentheses this function n, right? So 2xy minus e to the minus 2y. 2xy minus e to the minus 2y times y prime. That should equal 0. And as we multiply this through, the y's cancel. So this first term is e to the 2y plus, now we multiply term by term, right? So this is going to be 2x e to the 2y minus this e to the 2y's are going to cancel, and this is just going to leave us with 1 over y prime. Okay, so you can work that out, and this is all equal to 0 still. Now at this point, this is our m with a hat, and this is our n with a hat, and we can check and make sure that it's truly exact, right? So if we've done everything right, then it should be, but let's check anyway. So dm hat dy, take the derivative with respect to y, we get 2 e to the 2y. Okay, dn hat by dx, well, this is going to be 2, derivative of x is 1, right? So this is 2 e to the 2y, and then derivative of 1 over y with respect to x is 0. So there we go. And now we subtract, look at that. This is 0, right? So this one is now exact. Okay, so how do we solve this exact equation? Well, we take our partial integrals, right, with respect to now, not these variables, but with respect to x for this one and y for this one. So psi is equal to the integral of m bar dx. So that's the integral of e to the 2y dx. That's just going to multiply by x, right? So this is just going to be x e to the 2y plus some constant function that could depend on y. All right, plus a constant function that could depend on y. Similarly, the same function, psi, the same potential function, is going to be equal to the integral of n bar dy, right? So we integrate this one with respect to y. So this is 2 integral, of 2x e to the 2y minus 1 over y dy. Okay, and so this one's going to be, the x hangs around, the antiderivative of e to the 2y is 1/2 e to the 2y. So this will be x e to the 2y, 2 over 2 cancel, minus the antiderivative of 1 over y is natural log of y. And then this could have plus some function of x, right? Plus some function of x. And so now we just compare. We take the parts that we need, right? We have this part for both of them. We have this function of y that needs to go here, right? And then this term, the constant with respect to x, that one we don't need because there's no function up here that we're missing that just has x's and no y's. And so our solution, after all this work, right, our solution is that psi of xy is equal to, just take the parts we need, x e to the 2y minus natural log of y, and this is going to equal to our constant. All right, so this is an implicit function for y. We could, rearrange to solve this one. Well, no, we can't because we have e to the 2y here. So this one has got to stay as an implicit function of y, and it solves not only the differential equation that we made by using our integrating factor, but it solves the original equation as well, right? So it solves this original equation, this implicit function of y. Okay, so that's the method of exact equations and integrating factors to make our equations exact if they're not given to us as exact equations. So we'll leave this one here, and I'll see you guys in the next one.